So today we have Ravi, Kiran, Chirravuri, and Jan Florjanczyk. If you please correct me if I butchered your names. Today they'll be so the talk will be about Netflix's unique culture that it gives us data scientists in terms of freedom. Data scientists at Netflix are expected to build, deploy, and operate large machine learning workflows autonomously without the need to significantly have experience with systems or data engineering. Metaflow, which is Netflix's open source ML framework, provides with abstractions to manage projects lifecycle end to end, leveraging strengths of the cloud in terms of elastic compute and high throughput storage. So our speakers are Ravi, who is a software engineer on the machine learning infrastructure team at Netflix with almost a decade of industry experience in building large-scale systems, and Jan, who's a senior data scientist on content demand modeling team at Netflix. So they'll be talking, I guess, for your intro. So take it away, guys.
Thank you, Ali. Hi, everybody. I hope you can forgive me if I have to run to the door to take care of a puppy that has decided to live with me while we have this talk. Yeah, thank you. So my name is Jan. I'm joined today with Ravi. Today we're talking about Metaflow. It is something that helps me work much more efficiently. I'm a senior data scientist on the content demand modeling team at Netflix. And the first thing I'm going to do today is tell you what that team is and what we do. So content demand modeling, we are generally concerned with two broad questions. The first of these is which existing titles universe of the entertainment universe are comparable and in what ways. You can think of this as like a graph relationships type area or problem. And I want to draw attention to the fact that we should have a blog post coming out soon about this work. So look forward to that on the Netflix tech blog. The second thing that we work on is the question, how large is the potential audience of a show and in which region? And this happens to be the area that I work on. You can think of this as a supervised regression problem. And I'm focused on solving this problem after a show launches. And like most regression problems, it's best if you try and solve it more accurately, and if you try and solve it more accurately earlier. That's usually a pretty good improvement. So I want to tell you about something that happened on our team a little earlier this year. So a little earlier this year, my team members, Ashish, Natalie, and I, we were wondering about exactly this question. Could we make the supervised learning or the supervised regression more accurate and more accurate earlier? And we had some discussions about it. We tried a few ideas on our own. We decided that there was a good chance of success, that if we invested in a new model, we could actually solve it. And initially, we kind of expected this to be the kind of project that we could make a progress on over the course of a quarter. And we definitely weren't thinking about putting anything in production just yet, how we would launch or anything like that. So we wrote up our plan. We sent out this memo, and the interest from our stakeholders was so overwhelmingly positive that we decided we wanted to do it much earlier rather than later. And we realized that right around the same time, there was a sort of a fresh coat of paint, a sort of a light way of putting it, going down on a bunch of internal tools, and we felt that it was very opportune to launch the new model at the same time as that, which basically meant that we had a 2-week time frame to go from almost 0 to 1 with model development and launch here. I'm sorry, this dog has never jumped on me like this. Okay, so let me tell you about 3 requirements that we realized we would have in order to execute this project. The first one was that we needed to iterate quickly. We had this 2-week time frame, and we had a long backlog of feature ideas to try. We had all these sort of ideas kicking around. We should try this and that, this and that. The second was that amongst the 3 of us, we had varying levels of context. Some of us were more senior and more experienced. Others were closer to what had already been done. Others had known experiments that had failed in the past. Some were closer to the engineering. Others were closer to the machine learning. And the third requirement that we had was that we wanted a fast path to production. not only did we need to get it done in 2 weeks, we also needed this model to exist in this ecosystem of internal apps, and it was a really critical part of business reporting. And doing integration tests against that is quite costly because the scores go through many, many layers before they're presented all the way at the end. So with these 3 requirements in mind, I went to Ravi, who is an expert in solving these kind of problems, and I put the question to him. Ravi.
Thanks, Jan. Next slide. Being the software engineer that I am, I wanted to see if there was a slightly different way to visualize Jan's constraints. So let's see. If I understood Jan's constraints correctly, he wants to iterate quickly on model development and feature engineering. Jan and his team have multiple ideas they wish to quickly prototype and figure out what might be the best route to pick. In fact, it would be incredible if we can empower our data scientists like Jan with the highest degree of freedom at this layer of the stack, since there are many excellent off-the-shelf libraries like PyTorch, TensorFlow, scikit-learn, and I'm sure data scientists probably have their preference depending on the task at hand. He also mentioned about wanting to have multiple collaborators like Natalie and Ashish with varying levels of context, some who might prefer working in a notebook just on the modeling logic and access Jan's data, while some others might want to make a copy of his whole workflow and then mutate it and try out some other ideas. Having multiple collaborators and the need for trying out different versions makes versioning a key concern to solve. Machine learning also involves a lot of experimentation, and therefore model operations becomes a pertinent question. Things like, how do you keep the code running reliably in production? How do we monitor its performance? How do you deploy new versions of the code to run in parallel with previous versions? The software industry has spent over a decade perfecting DevOps best practices for normal software, and we're just getting started with data science. Lastly, he simply mentioned wanting a fast path to production to get a basic version out. While this sounds simple enough as a constraint, taking a machine learning idea to production is more nuanced, involving a few pieces of infrastructure to say the least. Jan has to access data from a data warehouse. This could either be a database or a multi-petabyte data lake. He might also want to write the data required for training into some common place so that his coworkers could then access it. Jan also mentioned he wants to create a simple enough benchmark model just for the others to sort of compare against. And this would need a compute environment to both crunch the data and produce a model. We could probably begin with something like a laptop, but this could also probably end up quickly scaling to like a large-scale container management system as well. Lastly, we will want an integration with a job scheduler to orchestrate multiple units of work and run our workload on a consistent schedule. Beyond these layers of infrastructure, Jan would probably also have to answer a few software engineering related questions. For example, how do you want to architect the code to be executed? You have this idea of a machine learning workflow. How would you want to break it down to the right level of atomic units of work that could run in parallel? How should we think about structuring the Python modules and getting them packaged properly to run in production? These set of questions outlined on this slide are not just specific to Jan's project. What we realized when we looked at several other data science projects at Netflix is that production-grade data science projects rely on a thick stack of infrastructure, as demonstrated on this slide. In our experience, now, given a choice, if I went to Jan and asked him, Jan, how much would you want to worry about the lower levels of the stack? I'm sure he would much prefer to stay atop this stack as much as possible. he probably wouldn't want to spend too much energy thinking about the software architecture or having a strong opinion about the right choice of infrastructure integrations. And would probably, as mentioned before, want to spend as much of time possible on feature engineering or modeling logic and iterating quickly on it. And conversely enough, this is the role where we as machine learning infrastructure can add a lot of value. We could take care of all the heavy lifting required with translating a data scientist's intent of a machine learning workflow to running safely and reliably in production, while integrating with all the relevant layers of the stack needed to do so. We could also afford to be quite opinionated about the decisions at the bottom layers of the stack and hopefully build a lot of software engineering best practices so that the data scientists can get them for free. To answer not only Jan's problem at hand, but also several other data scientists at Netflix, we built Metaflow, a human-centric framework for building and managing real-life data science projects. It's been battle-tested at Netflix for over 3 years now, and is used for an array of machine learning and data science use cases related to catalog performance and content production. Metaflow beautifully packages all of its offerings into one simple library that is now available open source for both Python and R, with easy integrations to the AWS cloud, giving you immense amount of freedom at the higher levels of the stack, while being opinionated about the lower layers of this infrastructure stack. Over the next few slides, I want to unravel Metaflow a bit further and present how we make it easy for data scientists like Jan to focus on their modeling tasks while providing simple, delightful abstractions to common data science challenges. The concept of a DAG, or a directed acyclic graph, is probably the first thing that you want to understand about Metaflow. Think of it this way. Jan has a machine learning pipeline as an idea, and he may want to break that down to steps. He would want to preferably deal with data preparation at first, then moving on to future computation, while finally rounding it up with training multiple models and see which one might do better. You can sort of see a DAG kind of mapping here. We also try to keep the Metaflow syntax as Pythonic as possible so that our users don't have to pick up a new DSL or domain-specific language and can quickly onboard to using Metaflow. Each step is annotated with an @step decorator, as demonstrated on this slide. And you can also express the transition from each node to its next using self.next. And we also try to just show a degree of static branching that is also available so that steps can run in parallel, like steps A and B on this slide. Core to any data science problem is data. We would prefer that Jan doesn't have to think too much about how and where to store model parameters, or how much to store, what to keep, what not to keep, or artifacts like the model itself for either serving or future debugging use cases. Metaflow makes the concept of artifacts as easy as writing to an instance variable, therefore self.x in this example. Everything is versioned and stored in our data store at the end of task completion. To keep our storage footprint low, we efficiently compress the data and store it in a content address fashion to avoid storing duplicate copies across multiple tasks. For those of you skeptical if this is sort of a scalable enough thing to do for your company or your use case, I can assure you that our AWS storage costs are actually quite low, even though we store everything on behalf of our data scientists. Here in this example, the task associated with step A stores x equals 4, while the task for step B stores x equals 5, in 2 separate locations in our data storage. In the join step, we actually provide our users with access to all the inputs, so both values of x in this case, so that they can decide which value to sort of take further and use. In Jan's use case, imagine the variable x being a machine learning model that he may want to finally end up training, or in fact, even a data frame containing the training data so that some of his colleagues could actually use the access to that and train their own model somewhere else. Okay, we spoke about data, and I guess Jan probably at this point can figure out how to both read and write data. Great. Now, I think it's important to sort of think about how can you run some of the computations on that data. Let's say Jan starts doing something on his laptop, but now things start looking good and we want to scale the idea on a full data set. Or maybe he just wants to train a resource-heavy machine learning model. Probably his own laptop at home might not work for this. Jan would probably just like it best if I could just provide a bigger laptop for him on demand, so that he doesn't have to worry about the perils of distributed computing just as yet. Metaflow, being cloud first, can easily achieve vertical scalability by simply leveraging the @resources decorator and @batch decorator in tandem. Jan might know best if he wants to train his model on a GPU, or how much memory maybe his data processing step might probably want at max. Therefore, we think it's helpful to just have him specify that, and then, as indicated here for steps A and B, and then Metaflow could take care of the necessary translation from what's specified for the step to actually getting it to run remotely on AWS batch with relevant resource requirements. Next slide. We also understand that at times, maybe a single box may not work for your machine learning workloads. Specifying a hyperparameter grid, for example, where you want to horizontally farm off compute to multiple subprocesses on your laptop or multiple containers on AWS batch, is something you might want to do. And therefore, we make this quite easy using our for each construct, which lets you execute n copies of the same step while feeding each of them a distinct input. So speaking about Jan's use case, another possible idea could be sharding his very large data set and using for each to process individual batches of data, for example. Before we almost run away with our workflow to production, I quickly want to pause and also highlight the need for dependency management. There are many excellent off-the-shelf libraries in Python to help with data science nowadays. You have your well-known TensorFlow, PyTorch, scikit-learn for machine learning algorithms, Pandas and NumPy for data processing, and probably you have a ton of exotic libraries as well, depending on the task at hand. Data scientists may not want to worry about this while prototyping, but it's definitely something you'd want to think about if you want to have your machine learning pipeline run reliably and consistently in production. For example, Jan wouldn't want his machine learning pipeline to suddenly start failing, surprisingly, when no new changes are made to his workflow. In order to achieve this, we leverage @conda to provide isolated, version, and reproducible environments with Metaflow. It is as simple as just specifying the libraries you might want access to, as shown here on this slide, and that's all you have to do while Metaflow takes care of all the rest to get you that environment on your remote container even. The last step in our journey to production is a scheduler integration. Once we have a workflow that looks promising at scale, we would want our data scientists to almost make 0 code changes and still be able to run on a consistent schedule using a scheduler integration. We've provided a reference implementation by integrating with AWS step functions, and written about our experience in the above link. Do check it out if you're interested more in this. Next, once you have a workflow running in production, Jan might have other ideas he might want to test out. He also mentioned that he might want his coworkers to also have their own workflows running or want access to sort of the data that Jan builds. Metaflow supports a first-level concept of versioning, where every task execution in every run for every flow for any user is versioned. To allow collaboration between people with varying levels of context, and probably some who are just interested to prototype in a Jupyter notebook, for example, Metaflow provides a Python client. You can easily use our client API, as demonstrated on this slide, to access either the latest run of yourself or a coworker's, simply using the concept of namespaces. While we won't get into more details, the concept of tags also makes it quite easy to annotate your runs with human-readable sort of placeholders to be able to quickly retrieve them later. Using the same Python client, you can also inspect the data within each task in case you want to use a notebook for debugging or a dashboard or monitoring purposes. On the topic of model operations, internally we've been thinking about how to interplay Metaflow for compute and notebooks for dashboarding and auditing purposes, but unfortunately this is not open source yet. This would allow Jan and his team to impose some safety checks while being able to train a model consistently to prevent staleness and still ensuring safety. Lastly, we have our workflow running safely and reliably in production. However, I think there is more of a cyclical nature to data science projects between prototyping and production, rather than production as a terminal goal. Since everything is versioned, stored in S3, tagged by a single metadata service, Metaflow makes it quite easy to switch between local scheduling on your laptop and a production environment using Resume. This feature is a key piece to iterating quickly, since you can easily reproduce your failures in a production environment safely in your user namespace, test out your ideas, and quickly push out a fix. Okay, I know I spoke a lot about Metaflow while hypothesizing how some of these features we've built could be useful to Jan's problem at hand. However, I think it's better you hear it from Jan himself how his experience with Metaflow was, and what features of Metaflow that he found useful and why. With that, the floor is lava. Oh, sorry. The floor is yours, Jan.
Ravi. So let's go back to that moment earlier this year, right around March, where we're in this 2-week period with my 2 coworkers, and we're trying to get this this model built and out into production very quickly. I'm going to show you how we use these components on the right-hand side here to achieve the goals on the left. And the first step in doing that was that I created something that I'm going to call the skeleton flow. So this is something I did. What is the skeleton flow? It's a simple flow that I can share with my team. It does all the feature preparation and large in-memory joins, and it runs on cloud infrastructure. So I don't have to farm a whole bunch of data preparation in my laptop. One notable property of the skeleton flow is that we realized that the problem we were trying to solve could actually be subdivided into a bunch of tasks, which is why you see that sort of cartoon of the fan out that we had, meaning that my coworkers, rather than having to iterate on all, n subtasks, they could iterate on just one. And so here I am with the skeleton flow using horizontal scalability to make subtasks and vertical scalability because those large in-memory joins are quite expensive. So then my coworkers, Ashish and Natalie, they like working in Jupyter notebooks, plenty of plotting, really fast REPL type interface. How do they get access to the data that I've prepared? And that is through the client API and the storage feature. They're able to simply pick a specific subtask and pull in the training data and the test data that we had all agreed on would be the sort of gold standard for our experiments going forward. A really easy operation for them, and the data loads really quickly because there's no sort of individual record transport happening. The other thing that happened over those 2 weeks was that we were able to use versioning. And I would keep iterating on the skeleton flow here and there. Sometimes I'd add more features. I'd run my own experiments. I'd clean up the data somewhat. And an easy way for me to push those changes over to Ashish and Natalie would be simply to point them to either a new run, a different tag, a different namespace, or just say, if you're already pointing to the latest one, just pull it in again, and you'll have what I'm using on my computer on yours. A really easy way to share the sort of state of the model as we kept iterating on it. So then we did launch the model at the end of the 2 weeks. It was a success. Since then, the 3 other features have kicked in for us. I mean, we're obviously running on a scheduler to have the flow run daily. We manage all of our dependencies with that @conda decorator. That's actually saved us a couple of times from weird package dependencies we didn't want to have to bump. And we've been using resuming flows because bugs do arise, and we do make changes and update the versions of the model. And when we get those bugs, we can resume them locally. So what would the 3 of us say if you asked us as customers of Metaflow? We've been customers of Metaflow now for, not customers, we've been users of Metaflow for about 2 years now. I'd say there's 3 things. The first is that we had accuracy wins, and that's always really important to us. In that 2-week sprint, we were able to increase our model's accuracy by about 25%. And really, the thing that allowed that to happen was that we were able to share the same training and test data without any questions asked. Like, we knew for sure we were working on the same thing. There's this pick up and go feel that we had when we were using it. There's no new DSL to learn. It's very Pythonic to write. And it means that our production code looks fairly similar to our experiments. There's very little to rework as you're going from one to the other. And you certainly don't have to invent completely new functions. And the last piece is there's very low ops overhead. The thing's been running. We got versioning and dependency management that help us go, from our dev to our staging to our prod environments, and this gives us a lot reliable deployments and runs. That's the story of us using Metaflow. Thank you, Ravi, for going into all the details, and thank you all for listening. Here's our contact info, and with that, we will open it up for questions. If there's any from the audience, please hit us up. I'm not seeing any in the session chat or in the polls. I don't know that.
Yeah, I think we might have delivered an extraordinarily clear presentation.
Way too clear. All right, make it murkier next time is the feedback. Got it.
Or probably, yeah, went over the head. But definitely, I mean, we can. Okay, we have one question.
From Alex asks, what are the underlying compute resources, Ravi?
So, as mentioned, we allow. So we have this sort of what we call a SciComp instance, but basically it's like a cloud workstation that you have that most of our data scientists initially use. You can sort of think of that as the local experience that they're used to, with decent sort of RAM and CPU constraints. But the other is we have a container management system called Titus, which is similar to AWS Patch, that the more heavier workloads can sort of run on demand or get a GPU access on demand, etc. And also the scheduler integration uses Titus underneath. So that's the setup that we have inside Netflix. Thank you for the question.
Yeah, thank you for the question. I will say that it might seem strange to use pandas instead. Like, one thing I mentioned is that we were doing large in-memory data frame joins. It might feel strange to use pandas rather than Spark or Spark SQL to do those joins. For the size of data that we work with, and I would bet for a lot of data that you tend to model on after you've prepared it, in-memory joins is not a terrible way to go. And you can iterate quickly on it. Do you use question from Rahul? Do you use Metaflow for running models and doing inferences in production? So we batch score the specific problem that I was solving, but Ravi, I think there's other ways to score models as well, right?
Right. Yeah. So yeah, thanks, Rahul. We do use Metaflow for running models in production. So a lot of times, like, you can train them. And then I haven't spoken about that piece today here in this presentation, but we also have what is called Metaflow hosting, which is essentially like a functions as a service paradigm, which can host sort of functions for our data scientists. And this could either be feature computations, or you can imagine the model itself. So that is the thing that is used for inferencing. Point to note, though, is that a lot of these use cases are non-member facing. Therefore, they are powering internal dashboards or other sort of business-facing dashboards. Therefore, this mostly works quite well. And the focus definitely is more around sort of ease of use and flexibility, more than sort of scale. Okay, more questions.
A question from Manoj, I hope I got that name right. Is it possible to execute Metaflow in a low latency fashion where all the data communication amongst the steps is done in memory without requiring expensive database I/O?
Yeah, yes, Manoj, yeah. I think we do have we have written both a local scheduler and you can also have a local data store that's just sort of implemented over your file system. So there is a way to run Metaflow in an all local mode, like where you don't have any external metadata, external database. The thing to note is mostly, if you want to collaborate with other people, maybe other coworkers in the same sort of organization, that's when the remote sort of integrations help quite a bit. So that's why they happen to be our default. But definitely the answer is yes for doing what you're asking.
And then one more question from Alex. When developing Metaflow, why did you decide to make this tool over existing tools such as Kubeflow?
This is a slightly tougher one. I should sort of add a disclaimer that I joined the machine learning infrastructure team probably 2 years ago, and Metaflow was built maybe slightly, Metaflow predates me a little bit. But I would say I don't quite know since when Kubeflow has been around, but with that caveated, there is a different machine learning infrastructure team at Netflix that has a more Java and Scala stack for the personalization use case. And a lot of the birth of Metaflow and machine learning infrastructure team that we have is due to like a lot of the sort of both cultural tenets of Netflix around freedom and responsibility that our data scientists have, and also the array of machine learning use cases that are non-member facing that this was meant to target. So we wanted something that can hopefully work under the freedom and responsibility sort of cultural component at Netflix, such that data scientists get power to use whatever tools they might want. So that's why Metaflow is not opinionated about what Python package you could use. Like people also use Metaflow just as a MapReduce, for example. So the framework is quite like in its core, like not machine learning specific, but we are also trying to build other features on top of the basic framework that are more machine learning focused. Like how do you collaborate with multiple people, or how do you string multiple projects together? So hopefully that answers your question, but I can definitely answer it offline if you really feel it's unsatisfactory.
We're going a touch long, but I was told that we could because everything is virtual. So we'll take one more question from Rahul. Does Metaflow also support dataset versioning and or model versioning? I mean, by virtue of everything being versioned, absolutely, like literally every single thing gets versioned and serialized to S3 or your storage layer. Like, yes is the answer, right?
Right. Yeah. So Rahul, one other thing to point is that a lot of our data comes from the data warehouse in S3, and therefore we already recommend quite a lot of best practices there, where we want people to sort of store, like version copies of the data, even the raw data in the warehouse, and but thereafter, everything you bring into Metaflow, like let's say Jan brings a data, like some raw data, does some feature computation, and this becomes like the clean training data, that could then just be serialized to S3, like using a data frame like Jan was mentioning. So that's what our data scientists do, but it's not exactly like we're also keeping a set of golden data sets version in S3, just to sort of hopefully read through your question.
One pattern that I follow is I have a training flow and a scoring flow, and the scoring flow has hard coded in it the run ID of the training flow. So for me, model promotion, there's a lot of different ways to do it, and I think every way is done somewhere at some point. But one way that I promote models is I will just change, I'll do a git commit basically and say there's a new training run ID that the scoring flow needs to follow. So that's another way to sort of maintain model versions. And you can tag, so you can also annotate things, with, for example, git hashes if you care. Okay, doggy needs to go for a walk. I think we'll need to wrap it up. Okay,
yeah, thanks for having us, and yeah, hope you all enjoyed the presentation.
Thank you, Ravi and John. This was amazing. Thank you so much.
Thank you for having us.
Always. Talk to you soon.
Cheers. Bye.
Thanks, everyone.